Hello engineering students, welcome to the video for week 21A. The picture on the screen right here is what Gil Addisons Desk currently looks like. It's honestly almost done. Got all the struts, everything's bolted together. The only thing that's not really in place yet is the actuator at the back, and I just need a couple more bolts that are the correct size, which I'll grab pretty soon. But things looking good. All the bits and pieces are completely glued that need to be. By the way, if you're wondering, all of these lines here are glued. Okay, stuff like that, like there, things like that. And then everything else is all bolted together. This is just sitting on a big flat sheet to represent the tabletop. It's clamped at the back here. This is the adjustment here, which lets the keyboard and mouse part go up and down. The computer itself sits right here, and then there is you can't really see it, but there's a couple of holes. There's a wooden kind of a strap clamp that goes across to anchor that down. And then, like I said, there's going to be an actuator sort of hidden in the back here, and that is what's going to make these things go up and down. So, it's coming along. And once I get that actuator fully in position, then I'll actually take apart the whole thing, and maybe I'll bring it to school again, and you guys can rub it with the special protective oil that I have, and then we can put it all back together and strap an iMac on it and see how it goes. So that's exciting. Then Mrs. Jones' project comes after that. And then I have another project in the pipeline from Mr. Mitchell that I said we'll get to him sometime before the end of the year. Won't be a rush job, but he's got a really cool idea as well that's sort of in line with the kind of stuff we've been doing. Okay, for this week, we are going to... Oh, that's not the picture I thought it was going to come up. We are really just going to try to review what we talked about in week 20B. So I'm going to summarize the whole video and, play this at 2 times speed if you want to. The whole video, because sometimes just re-saying something like 5 or 6 days later is just the very best medicine, and it just feels a little easier next time. I am a student myself. I am currently trying to get better in my Spanish to, just take one thing that I'm trying to learn right now. And, I just went back and listened to some podcasts that I hadn't listened to for about 2 years, and they seem so much easier now. So that is how learning works. You just get better as you go. So we talked about the fact that all rigid materials are kind of springy. Okay, they all kind of stretch and act like a spring, and that we can define these using 4 terms. Define these properties using 4 important terms: stress, strength, strain, lots of words, and then elasticity. Okay, those are like the vocabulary terms that help us talk about the springiness or the stiffness of materials. We said that all of these properties are intensive properties because they don't change with the size or shape of the object. If you have a piece that is twice as big, you don't suddenly have twice as much of elasticity because it's still made out of the same wood or steel or whatever it might be. Okay, the ultimate tensile strength of pine wood doesn't change just because you have a bigger piece of pine wood. That's what an intensive property is. The opposite of that is extensive properties. Okay, we said that stress is measured in pascals, capital P, lowercase a. 1 Pascal is the same thing, remember, as a Newton per square meter. And the definition of stress is that stress, that's lowercase sigma, is defined as force over area. Okay, you take a force, you divide it by a particular area. That is the stress on that object or on that part. We talked about the strength. Strength is also measured in pascals. And strength is simply the point at which the stress is going to break or even, let's say, damage a certain material. Okay? So we're going to break or damage. There is more to the tensile stress story that I haven't really told you about beyond just the UTS, the ultimate tensile strength. But we probably won't do that on this lecture. By the way, the ultimate tensile strength of steel, that's how we can write that, UTS subscript steel, is about 1,000 megapascals. If I wanted to, I could write 1 gigapascal for that. All right, next one, we had strain. Strain, we said, has no units. It's kind of like a percentage. Strain is defined with this formula. Little epsilon, lowercase epsilon, equals delta L over L. Okay, strain is the change in length divided by the original length. Sometimes, I didn't say this last time, sometimes we put a little zero there, a little subscript 0 to talk about the original length, like 0 as in, at time equals 0. Before the experiment started, this is how it began, and then we stretched it. That's kind of optional. I think everyone knows what you mean if you don't put that. And strain is all about saying how much stretch, that's the delta L, did the piece experience compared to the original length. All right, elasticity. Yes, I am going to keep on drinking water in the background, if you're wondering. Elasticity is also measured in pascals. How about that? Everything is measured in pascals or does not have units. And elasticity is the connection between stress and strain. And here is the formula that's very important. Stress equals E times epsilon. Okay, stress equals Young's modulus times the strain. And elasticity is a measure of how stiff the material is. Now, be very careful in your language. It's not about how strong a material is. It's about how stiff it is. Not about when it breaks. It's about how much it stretches when it gets stressed. Okay, so you can have the same stress applied to a piece of wood or a piece of aluminium, and they will stretch different amounts because their elasticity is different. All of that says nothing about when it breaks, just about how it deforms. We also pointed out that this is actually an intensive parallel to the Hooke's law that we already looked at, F equals kx. Okay, in both cases, what you're really talking about is a load equals the elasticity times the deformation. Okay, that's the concept. And then it manifests itself as either the intensive one, which is more focused on the material, like is it steel, is it wood, is it cast iron. This one is the extensive one, which focuses more on the particular piece. So this piece of wood right here that is this size and shape. This aluminium Coke can, this particular one with this size and shape will behave with this particular K value. Okay, so this one is kind of the general one. Oops, let me say that again. This is the general one focused on the material. This one is the specific one focused on the object and doesn't actually really care what the material is. All right, that was all this review. And I felt that 10 minutes of review was actually a worthwhile thing to do because I did dump a ton of bricks on you and I knew that you didn't have an assignment that would match to it until this week. So this week's assignment will be a bunch of practice problems just like the ones that I'm about to do. There's Gil's thing again. Let's all look at it. That's cool. It's fun to design something and see it emerge. I never get tired of that. All right, here is our first problem. Let's see. All right. Why don't you get... Yeah, let's move it over here. Why don't you get a calculator? Because I do want you to do this alongside with me. Little practice problems, okay? Remember, the very best practice you can do here, it's kind of like how I learned my Spanish, is you hear something being said, then you pause it, pause the playback, and then you try to respond or repeat or whatever the exercise is, and then you press play again. It takes a little bit longer, but you get way more out of the deal. You don't really learn stuff until you get forced to have to describe it, put it into concrete terms. So you might want to pause the video and do calculations and then press play and see if you got the same numbers. Okay, so this piece of pine wood, firstly, has dimensions of 40 millimeters by 90 millimeters. That is what it'll say if you're buying it off the shelf in Australia. Over here in the good old US of A, we will call that a 2x4. And let's say that this particular 2x4, oh, that's a horrible arrow, is 1 meter long. Okay, 1 meter, 1,000 millimeters. All right, that's some basic information. Let me tell you some more stuff about pine wood. The Young's modulus of pine, if you look it up, happens to be about 9 gigapascals, which is a very low number. Okay, 9 gigapascals. You compare that to the 200-ish for steel, the 70-ish for aluminium, and 9 suddenly looks pretty wimpy, because it is. And remember, that's not how strong it is, that's how much it stretches under load. Okay, and let's give you something else. The UTS of pine, that is the stress at which it snaps when you pull too much on it, is about 40 megapascals. Again, compared to steel's 1,000-ish megapascals, that sounds pretty weak. And that number is more what people think about when they say how strong a material is. So let's try some things. We're going to say, let's apply 500 newtons of tension. Okay, that's like the scenario. And let's calculate a few things. Firstly, what is the stress being created? Did we reach the UTS, the ultimate tensile strength? That's an important question. And then when we do this to it, our 500 newtons, how much does this piece stretch by? Is it noticeable? Is it a lot? Is it going to deform whatever it is that we're building, like a house? Is it going to be a problem? Let's do these one by one. This would be a good time to pause if you think you are really confident. Otherwise, you may want to just keep listening. Okay, how much stress? All right, stress is force over area. So we have force of 500. What is the area? Well, let's put everything in meters. You'll be glad that you did. 0.09, 0.04. That is the correct way to interpret 90 millimeters and 40 millimeters. Okay, because there are 1,000 millimeters. So I have moved the decimal place 3 times. Check this out. I'll do it the first time for you. If I have 90 millimeters, I'm going 1, 2, 3. Okay, that's where the decimal goes to because there are 1,000, 3 zeros, millimeters in a meter. Okay. I'm just going to jump in and do the calculation. I think, if I'm not mistaken, I think you can see my calculator on the screen with this particular new software that I'm using. That's cool. I guess I should be careful what I bring up on the screen. 138,888 point. Lots of eights. I'm going to say 139 kilopascals. Okay, let me go back to the calculator so you can see that. I'm interpreting that as 139 kilopascals. The kilo is the 1,000 multiplier, and I rounded off to 3 significant figures here. 139. I do not care about those 8s. Not one little bit. All right, we've answered that first question. What's the stress? Now, next question. Did we reach the UTS? 139 kilopascals. Compare that to the ultimate tensile strength of pine. And, you know, here's one way to compare it. We could say we have 139 kilopascals to 40,000 kilopascals. See how it says 40 megapascals up here? Well, 40 megapascals would be 40,000 kilopascals, because mega means million, kilo means thousand. There's 1,000 thousands in a million. Hope I'm not confusing you. But here's one way. Obviously, we're good. We're totally fine. But we have really only reached, let me times that answer by 100, 0.3%. Okay, I times by 100 because I converted it to a percentage. Okay, I did the division. I times by 100. That gives me 0.3%. If we pull with 500 newtons of tension, we're only 0.3% of the way to snapping this thing. Wow, it can carry a lot more load. Now, how much stretch? Okay, well, to do this, we're going to bring out our intensive Hooke's law. We're going to say we got 139 pascals. I'm going back to base units here without the kilo or mega multipliers, because then everything is in the same language. Or I could put it all in kilo or all in mega. Young's modulus is 9 gigapascals. That's 9 billion times the strain. Okay, and maybe then as I tap in the calculation, since you're just looking over my shoulder, I do save a little bit of time by knocking 3 zeros off my calculation. Because it's a fraction, I can wipe 3 zeros off the top and off the bottom as I do it. You see that on the screen right there, and I get the same answer. It's a little faster. Oh, scientific notation. Okay, we can handle this. 1.5, okay. I kind of missed that number actually. 1.54 times, okay. Now, please understand, calculators often give this result an E with a -5. That means times 10 to the -5. It's just the way that computers deliver results. I don't know why they couldn't just make it show proper scientific notation on the screen. Some calculators do. That, again, same sort of principle. You're going to go 1, 2, 3, 4, and then, you know, just bump the decimal 5 places because of the -5. Remember, there are no units for strain, but there it is. Actually, you know, we found the strain, but I'd actually like to sort of see how much it's stretched by. So if that is the strain, remember, strain is defined as the change in length over the original length. So I would actually like to see what was the change in length. I think that is a way better answer to give to someone. If they ask you what the stretch is, telling me, well, the strain was 0.0000154, that doesn't help me a great deal. But if I run it through the strain definition, which is this right here, that's the definition of strain, and I rearrange to solve for delta L, the change in length. Okay, this is what we're saying. We're saying that this thing gets a little tiny bit longer. Little tiny bit longer. And that's delta L right there. Change in length. Little tiny bit longer. That I can actually use. So I get my number. It's still on the screen, so I'm just going to leave it there on the screen. I'm going to multiply it by the length of the piece of wood, which I said was 1 meter. times 1. That was easy. I get the same thing. So the change in length was very easy in this case. We are measuring here in meters. Okay? Because I typed in 1 meter for my L, my delta L is also measured in meters. I could multiply that by 1,000, which actually just means knocking 3 zeros off. And that would give it to me in millimeters. That might be helpful. Okay. A millimeter is a small gap between your two fingers. It is on the screen. If you're playing this on, I guess I can't really draw on the screen because it completely depends what screen you're playing this on with the aspect ratio, but that's a very small amount, okay? Very small, that's less than about 1. What am I trying to say here? It's 1.5% of a millimeter. Nothing. You wouldn't see that. Now here's a follow-up question with all of this practicing, calculating. What would it take to break it? Okay. New question. How do you break this? How do you get it up to the breaking strength? Well, you go once again to your ultimate tensile strength for pine. We said was 40 megapascals. You run that through your stress formula. You say, 40 million pascals of stress. The force is what we're going to try to solve. The area we have, well, I guess we never worked it out, did we? The area was the 0.09 times the 0.04. Okay, 0.0036. 0036. So when we multiply that by 40 million, we get 144,000. It's like a quote from the Book of Revelation. 144,000 for a force, and that is measured in newtons. Okay? So you would have to apply 144,000 newtons of force to this humble little 2x4 made of pine before the thing would just snap like a toothpick. And I'm talking snapping in tension. You're pulling on it. That is a lot of force. 144,000 newtons is that many kilograms. And because we're in America, that many pounds. 6,500 pounds. A lot of pounds. It's hard to find 6,500 pounds these days just lying around. You could hang a good-sized truck off one piece of 2x4 and it would, would not break. That's comforting. Okay, let's keep on going here. Different material. I'll take a drink of water. This is structural steel. Structural steel has a Young's modulus of about 200 gigapascals, according to the website that I looked at. And it has a ultimate tensile strength of about 400 megapascals, quite a lot more than our dear little friend 40 megapascals over here. 40 compared to 400. Steel is about 10 times stronger. And actually, that's kind of surprising how good wood is, isn't it? You probably wouldn't think that. Steel seems better than that. You're better than that, steel, but no. Okay, you want to design a rectangular strut. Okay, or actually, let's say square. Sorry. So you can design a square strut. That is the worst drawing I can possibly imagine. That one's going to haunt me in my nightmares. Let's get at least a little bit of, you know, isometric angles here. Okay, you can design a steel strut. It's a square cross section, and we know that this thing has to span across 4 meters. Okay, like some of those big beams in that picture, that may be spanning 4 meters. It's hard to tell scale. We also, let's say that we know this thing needs to be able to handle 2 meganewtons, 2 million newtons. That's a lot of newtons. 2 million of them. That would be a typical sort of thing for a steel structure to carry, though. So here's a question for you. If you know that this thing is going to be a square cross-section, here's just a picture of the cross-section by itself, looking end on. You know what, let's make it a little bigger than that. Let's see here. And we can even use the grid to help us. Let's call these distances, well, x is good, isn't it? X, and because it's square, both sides are x. What's the definition of the area? X squared. Feels like a good middle school math problem right there. So if you want this thing to like exactly handle 2 million newtons, how big should you make that square cross section? Okay, how big should you make it? That is the question. Right there, you could pause the video and work it out. Here we go. You are going to use your... That's an ugly... Sorry, something's happening here. There we go. Stress equals force over area. We know that the stress that we can handle, the one that we're designing to, is 400 million pascals. The force that we are applying onto it, and you know, let's say we have that because we worked it out. We did like a truss calculation or something, and we found, oh, there's 2 million newtons on this member, and it's 4 meters long. That's the background to this story. We're saying, what area is that going to be? There you go. That's the calculation. It's really just a, you know, kind of a one-liner. We're going to divide 2 million by the 400 million, and you'll forgive me if I just do 2 divided by 400 and skip all those nasty zeros. 0.005 is our answer. Now, what is that measured in, ladies and gentlemen? If you said meters squared, you'd be correct. And, you know, even the fact that we're talking newtons, we're talking stress. Stress is newtons per square meter, so it's already hidden in the pascals terminology. Even a newton is actually a kilogram times a meter per second squared. So even though we haven't seen meters directly in the problem anywhere, they're lurking in the shadows of every unit that we encounter. And that's the beauty of the SI system. It's all internally consistent. Now, if we know what our area is needing to be, but we don't really know our side dimensions. Because the area is x squared, okay, each side length over here is x and x. That is where we take the square root of both sides. And you say to yourself, self, here I go, 0.07, ooh, that almost looks like this, no, maybe not. I was going to say, it looks kind of like sine 45, cosine 45, that divided by 10. I don't think it is. Or is it? Hold on. Keep that number, folks. 0.0707106 cutting off. Hold on. Wow, it is the same number. How about that? The square root of 0.005 is the same number as sine 45 divided by 10. Sorry for that little distraction. 0.0707, let's say that. And that is measured in meters, which is not a real convenient length measurement for that kind of work, by the way. If you're describing that in a drawing, you might give the length as 4 meters, but you certainly wouldn't measure like cross sections and detailed stuff in meters. You're going to measure that in millimeters, which means you're going to move the decimal place. Here, I'll show it to you here. 1, 2, 3 places. So that is going to be 70.7 millimeters. Milli is a thousandth. I was about to say a millionth, sorry, a thousandth. So that is our answer. 70.7 millimeters, 70.7 millimeters. By the way, 70.7 millimeters, that's a little less than 3 inches. Okay. Very, very roughly about 3 inches, just to give you a sense of the scope. So that means if you can imagine about a 3 inch by 3 inch square that is 4 meters long, that's like more than twice my height. That piece of steel, that can handle 2 million newtons of load in tension. No sweat. Actually, it's going to just be starting to sweat and just starting to break at that point. So you don't want to take it to that load. So when we do design to, like, say 2 million newtons, we're assuming that the actual load in service is more like 1 million maybe. And so we've already doubled it, and now we're designing it to handle double what we think is going to happen so that we know that it's very safe. Okay, another question here would be, very natural, like, that's all well and good. I'm glad that thing is designed to handle it, but how much is it going to stretch by? How much will that particular piece of steel, that one we just designed with the 70.7 millimeters, how much will it stretch when it experiences the 2 meganewtons? This would be a great place to pause and see if you can work that out by yourself. Here is the solution. We use the intensive Hooke's law. Stress equals Young's modulus times strain. Let's see. We know what the stress is. The stress, in this case, we said it is the actual ultimate tensile strength. That's what we're designing to in this case. So we'll just use that. 400 million pascals of applied load. For the Young's modulus, the E, it's steel. It's structural steel, which I told you in this case, call it 200 gigapascals. Steel is pretty consistent. It's always somewhere between 200, 210. There's 200 billions right there. And then we have the strain, which is the unknown thing here. Let's see. We divide by that 200 billion. Again, I'll pull my little quick trick here, just cancelling off zeros as we go. I could have taken off more zeros, but it's just typical to sort of just grab those grouped thousands. 0.002 is my strain. Okay, there it is. That's the strain. Okay, remember, that's the strain, which is a relative measure relative to the length. So let's see what it actually stretched by. If the strain was 0.002, I multiply both sides by L, that will get me the change in length. Remember that delta L is like 1 unit. That is one thing. They stick together. The delta, it's almost like a subscript modifier or a, I don't know, like a vector symbol that's above, like how we would do things like F with a vector symbol above it. That's what the delta is like. The delta is more like a modifier on the L. It's not a thing by itself. Okay. The length, we had a length of 4 meters. So we do 4 times 0.002 is our delta L, which is 0.008. Now, don't forget, this one is actually measured in meters now. That is an actual change in length. That is no longer the strain ratio. That's a hard and fast measurable measurement that you do with a ruler. If you want to put that into more convenient units, you go 1, 2, 3. There are 3 decimal places to jump by, and you get 8 millimeters is your actual stretch. 8 millimeters is very visible, okay? If you had a 4 meter long piece of steel, even though it's like 3 inches by 3 inches solid, if you could hang the 2 million newtons off that, which is what it takes to break it, right as it was breaking, it would have stretched by 8 millimeters, okay? Very visible. You actually see it stretch. It looks almost like putty. It tends to kind of narrow down. It kind of sucks in a little bit as well. That's called necking a piece of steel. An engineering scientist will say that the steel is necking. It gets narrow before it snaps. Like here is a piece of steel. You clamp it on both sides. This clearly is not a 4 meter long piece of steel. And you start pulling on it with your test equipment, and then you find, as I said, as it gets pulled, it actually kind of like sucks in a little bit, and then you might even make some like little noises, and it seriously looks like Play-Doh or putty or something, and then all of a sudden just goes bang and pops, and there's a nice little break there. If you join an engineering school, that'll be an experiment you would do in your first or second year of classes, guaranteed. Breaking stuff, measuring it. Okay, the last example to keep getting you familiar with these terms and how to use them, prepping you for the assignment, is a piece of human bone. This is supposed to be, well, it is. This is a picture of your humerus. Now, I don't know how you are on your human bones, but that is the bone in your upper arm, okay, where your biceps are, and shoulder on one end, radius and ulna on the other. Usually the people who know the names of bones are the people who've broken bones, I find, but hopefully you haven't broken your humerus. By the way, I hope that you know that when you hit your funny bone on your elbow, that's at the end of your humerus. So that is a good way to remember that. It's like a silly dad joke that scientists have bequeathed upon us. Okay, bone has a Young's modulus of about 18 gigapascals, depending on which website you're looking at. And it's got a, let's see, I'm going to write this a little bit different now. This is a, I'm just going to write it like this. I'm actually going to do compressive strength this time. We've only talked about tension in regard to everything, just because I was trying to keep as many variables fixed as I could while I taught this to you. But all these principles about Hooke's law, they all work in tension and compression, but you do get different failure strengths for tensile and compressive loads, usually. Okay, the Young's modulus usually sort of works the same. It's usually about the same amount whether you're stretching or squeezing, pulling or crushing, but the compressive strength is actually very sensitive to whether it's been pulled, stretched, squeezed, slid, scraped, whatever mode it is. So this is specifically the compressive strength of bone, because when bone breaks, it usually breaks in a compressive way. It usually gets crushed. It doesn't usually get pulled to breaking point, because your sockets and joints pop before that happens, I guess. So anyway, let's say your humerus has an average diameter. Okay, this is the diameter. There's the diameter symbol of 25 millimeters, roughly. You can see it varies. Let's be a little tricky here. It's hollow, right? That's where your marrow lives. That's where your blood cells come from. So this is the outer diameter. Let's say your outer diameter is that, but let's say you've got an inner diameter as well of about 15 millimeters. Okay, so your humerus is roughly like a circular pipe with an outside diameter and an inside diameter. And as far as length goes, let's say the length is roughly 300 millimeters, about 12 inches long. That is about what it is, depending, of course, on your size and shape. A shorter person has a smaller humerus typically than a taller person, unless you got like weird long arms. Let's look at the cross section here. If we were to cut the bone, and I just can't resist drawing someone cutting the bone here. Is that a bit morbid? Cutting the bone with like a bone saw. Okay, there's the stuff. If you were to cut that bone in half and look at it end on, as I said, we're going to pretend, no, let's make it bigger than that. We're going to pretend that you are looking essentially at a hollow pipe with an outer diameter of 25 mil and an inner diameter of 15 mil. So what I would like to know is what is the actual cross-sectional area of the bone. We did do areas and sections in first semester. We did some kind of complex shapes where you have to add and subtract areas and zones of rectangles, circles, triangles. We did spreadsheet calculations. So this is actually well within your purview. You might wish to calculate that area right now. Pause the video. I dare you. If you didn't pause it, or if you did and you're back, the area is the outside circle minus the inside circle. Circles are pi r squared. Careful with your diameters and your radii. I'm also going to collect the pi as a like term, as a common factor on both terms, and I'll grab that to the outside. The outer radius is 12.5 and the inner radius is 7.5. I am halving the 25 and the 15 to get that. Okay. All I'm doing, hope that wasn't too fast for you, that's the outer circle as though nothing else existed, and I'm subtracting away the inner circle. Okay, and then I'm just looking at algebraically, I collected the pi and I put it out there, and then I filled in the radius instead of the diameter, which is half. Now don't forget those little squares up there. They are easy to forget, even for the seasoned engineers and mathematicians among you. Oh, that's too easy. That feels wrong. All right, we'll take it. Exactly 100 somehow. And then, of course, we're going to multiply that by our old friend pi, and we get 314, and we'll keep it at 3 significant figures. And that is millimeters squared. Now, this is a little bit of a problem, maybe. We're in millimeters and not meters. I'm debating where to go with this. There are a few different things I could do here. Well, let's do it this way. Let's do it this way. I'm going to teach you a little trick. We've done a few practice ones already, pretty straightforward. I'm going to teach you a trick on this one. So let's say, I'm going to say the person is holding a weight. Let's say you're like lifting a weight above your head of 150 newtons. Like you grab like a big, I don't know, sand bag or a small child or a chair with a person on it because you're at a Jewish wedding, and you lift them up above your head so there's a compressive force down on your humerus and all of the rest of your body, in fact. So let's see, what stress does this create on our bone? What compressive stress? Well, just because things are getting a little crazy at this Jewish wedding doesn't mean that the stress formula changes. And just because it's compressive and not tensile doesn't mean the stress formula changes. It's still just the same. So we say the stress is equal to the force, 150 newtons, divided by the area. Now I'm going to do what I said I'd do. I'm going to pull a little trick here. I'm going to keep, instead of going to meters from millimeters, I'm going to work in newtons and millimeters. And here's what's going to happen. Because there are 1,000 millimeters in 1 meter, and because there are then 1,000 times 1,000 millimeters squared in 1 meter squared, because 1,000 times 1,000 gives you 1,000,000. You see that? So, okay, because there's a factor of 1,000 now between millimeters squared and meters squared. If you leave the units in millimeters, then you actually can run ahead and do the calculation just like that. 0.48. Let's call it 0.48. But your units for your stress are actually in megapascals, million pascals. All right, catch that again. Because there is 1,000,000 millimeters squared in 1 meter squared, because of that fact, if you work in millimeters squared for your areas, you get 1,000,000 times too big of an answer. In other words, you're getting megapascals. Okay, million here, million here. It actually works out just fine. You know, if I had instead done 150 newtons divided by 314 million, 150 divided by 314 million, I would have, hold on. What am I doing? Oh, I'm sorry. I went the wrong way. Apologies. I'm sorry. That's not 314. I need to take my decimal the other way. Why didn't someone stop me there? There we go. I get 477,707 pascals, but then if I divide that by 1,000,000 to go to megapascals, there it is, 0.48 megapascals. Okay, so one more time. If you work in newtons and millimeters squared for your area, your answer is in megapascals. Engineers actually typically do that because parts that you work with are usually designed in millimeters, and megapascals is the range of what stresses and strengths and even strains, sorry, not strains, Young's modulus are in. So it actually works quite nicely. Most people aren't working in pascals and meters. All right. 0.48 megapascals. Back to the main story. Are we okay with that? Well, the compressive strength of bone is 170 megapascals. Lifting up your sand bell above your head is only creating about half a megapascal. So you are only like, a 34th of the way to breaking your arm in compression, which is good news because, people lift heavy things above their head all the time, and you can't be breaking your humerus in compression every time you lift your 7-year-old onto your shoulders to give him a piggyback ride. Just can't. Wouldn't be any good. Now, how much weight could your humerus handle before it got crushed? Well, that's a fairly easy question. We say it can take 170 megapascals. We just said that. It's right up there. The area doesn't change. It's 314. We're working in millimeters here. Millimeters and megapascals. Okay, megapascals here. Newtons here. Millimeters squared here. So all those units actually speak to each other. And here we go. We are going to be timesing 170 by 314. Where are we? 170 times 314. And we get 53, rounding off, 53,000 megapascals. No, I'm sorry. Check that, 53,000 newtons. Sorry. Forces in this way of doing it are in newtons. Or if you prefer, as I do, 53 kilonewtons. Now, 53 kilonewtons, we divide that by 9.8 to get back to kilograms. And then if we divide it by 2.2 to go to pounds, that's 2,500 pounds. Your humerus can support about 2,500 pounds, like a Volkswagen Beetle before it crushes in compression. Now, other parts of you will get destroyed before your humerus crushes in compression. That's not the most likely thing that will happen. Most likely thing is that it'll fall on your windpipe and then you'll stop breathing. But, sorry, I'm being kind of morbid. Your humerus will be just fine. That's the moral of the story. Okay, well, hope you can see I've just been doing the same thing over and over again in slightly different ways with our bone example, with our structural steel example, and with our pine wood example. We're just recycling those same formulas every time. The stress formula, the definition of strain, and the general Hooke's law formula. Hope you're getting the hang of it. Good luck on the assignment, and please do find me if you need some support with that. Over and out.